Well, hello again, Daniel and Blake. Let's take a look here at 17.2. It's our last video for the week. So we are going to be looking at Stokes' theorem. So we had Green's theorem in 7.1. We're now going to look at Stokes' theorem, which is actually an expansion of Green's theorem. It's really an expansion of Green's theorem to 3 dimensions. And it does get kind of messy. I'll just warn you that ahead of time. The good news is that number 1 and number 3 shouldn't take you very long. I make no promises about 5, 7, and 9 though. All right, let's take a look at what we've got. First, let's talk about our concept of curl. So we introduced that in the last time. Let's look at curl, particularly curl in 3 dimensions. So what we see, curl, which we just write as the curl of a vector field here, that's going to be equal to nabla crossed with our vector field. And probably about this time you're asking what on earth nabla is. Nabla is the vector, the derivative with respect to x, the derivative with respect to y, and the derivative with respect to z, where those are the individual components. So that's what we get for our nabla. And we cross that with our vector field. And we get another vector, which is our curl. Now, we can do it that way. Another way that we can go ahead and we can do this is there is a formula for this, and it does work well. And the problem is it is not the easiest thing to memorize. Now, it's easier to find the curl using the formula that I'm going to give you right now if you can obviously look at the formula. But if you can't look at the formula, you're going to have to memorize it, and I've got a couple tricks that may help you with it, but it is still something that's not the easiest in the world to memorize. So here's our formula. Remember the curl of f, it is a vector, and so we get this expression here, this vector here. Now, I think the easiest way that I can help you keep straight what you're doing here is if you remember the cross product here, this will help you. So when you first cross, what you're doing is you notice you're not going to have any derivatives with respect to x. So notice we have no derivatives. So for the x term, there are no derivatives with respect to x. And the y comes before the z. So we take the derivative of the z term with respect to y minus the derivative of the y term with respect to z. That's our x term. Now this one here, we reverse this order because remember when we're doing a cross product here of vectors, we subtract the middle term or the middle component. So what that does is that changes the sign of each of these. So normally you'd think of as doing x first and then subtracting z, but because of the minus, we switch it up. So what we have here is if you think normally it would go the derivative of the z component over x minus the derivative of the x component over z, because we always, here we go yz, here we would go xz, notice no y's when we're doing the y component, but since it's minus, we have to switch the order. And then here where we're doing the z, notice there's no derivatives with respect to z, and we do go x and then y, and so we take the derivative of the y component with respect to x, the derivative of the x component with respect to y. That's the easiest way that I've been able to figure out how to memorize that. That would be the best I could offer you. The good news is chapter 17 is only 3 sections, so it's not like you're going to have that much you have to memorize. Okay, so let's go on. Let's look at this, what Stokes' theorem actually does. So it incorporates, obviously we're talking about curl because it incorporates the concept of curl. So what we see here is when we have this particular situation where we have a closed curve. So we have the integral of this closed curve over the vector field f dot ds. What that's going to be equal to is it's going to be equal to the double integral of the curl of the vector field f dot ds, where this is actually our surface. And so this becomes an advantage when this line integral is very difficult to compute. Remember, this is the advantage we had of Green's theorem. There were times where this line integral was really messy to do, but it wasn't too bad to integrate this. And if we can get the curl here in a relatively simple expression, and these become simpler limits when we look at the double integral as opposed to this this linear integral with very complex expressions, it can be an advantage. So that's basically what it comes to. All right, let's look at some examples. So first, number 2 is very simple. It just gives us this vector field. Number 1 and 3 are going to ask you to do the same thing. It says, find the curl. So if we want to, we could go ahead, find nabla, do the cross product, but it's probably easier just to have this memorized. So if we do that, we know the curl of f is going to be equal to, and what we'll do here is, following this formula here, we take the derivative of the, so to find the x term, remember it's just like we have no x term, and so we'll take the derivative of y first, so we'll take the derivative of this with respect to y, which is just 0, minus the derivative of this with respect to z. Well, notice what happens here. This would be y, this would become negative y over z squared, but it's minus the negative, so it becomes positive. So we just have y over z squared. For the next term, we know we're going to get the y term, so we're going to not have any derivatives with respect to y. Normally, we would go the derivative with respect to x, then the derivative with respect to z, because we derive with x before z, but we're going to reverse it because it's that middle term. So we take the derivative of this with respect to z, which is just 0. And then we subtract the derivative of this with respect to x, which we would get the same thing. We would get a negative z over x squared. So minus the negative becomes positive, so I get z over x squared. And the last term, once again, we're doing this, no derivatives with respect to z. So we would take the derivative with respect to x first, which is this term, which is just 0. Then the derivative of this with respect to y. So it would be 0 minus, and the derivative of that, the 1 over x just becomes a constant. So we just have negative 1 over x. And that's our curl. Pretty straightforward. I don't think those should give you too much difficulty. Now for the ones that'll be a little bit worse. Number 8. So number 8, what wants us to do is basically verify Stokes' theorem. So what it wants us to do is calculate this integral of the line integral here and calculate using this and verify that you get the same answer with both. So here's our vector field. Here's our surface. And we know it's where z is greater than 0. So we basically have the upper hemisphere here of this unit sphere is what we've got. So first let's go ahead and let's consider this is what we're trying to show. We must show that this is equal to this. So in other words, verify Stokes' theorem. So let's do this line integral first. So what we have to start with there is we have to, this is going to be part A. We have to parameterize the boundary curve. So doing this here, we've got this curve here, and the boundary curve of this, if you want to think of it, if you look at your surface, you can take a look in your book at boundary curves. They're found, good pictures of boundary curves are found, figure 1 and figure 2 give you a good idea of boundary curves. Something like a sphere would not have any boundary curves, but this is a hemisphere, so it does have a boundary curve. It is the it is essentially the circle, the unit circle in the xy plane. So this is our equation here of what we want to parameterize. So notice our z is 0 in this case here, and we have a circle. So when we go to parameterize this, we are going to use we'll use the function gamma to denote this. Similar to our g function, but our g function we're usually using for when it's a surface, like we do a lot of g function in terms of g of u of v, or g of theta phi, or g of theta r, something like that. So this is our gamma. It's going to be in terms of t. So parameterizing this, we know our x component is going to be the cosine of t. Remember, we could say 1 cosine t, but it's cosine t. The y component is going to be the sine of t, and our z component is 0. And that's where we know t ranges from 0 to 2 pi. That would give us our complete curve. So now we're going to go ahead and we're going to calculate this integral here. So in order to do that, we're going to have to take our parameterization and put it into our vector field f, and we're going to have to multiply that by our derivative of our parameterization. That's our, we're working with our, that's our ds there. So doing that, we see that first off, this is our vector field here with our parameterization plugged in. And then we've got our derivative here of our parameterization. So we're going to take our derivative of this expression right here. So that's going to be dotted with our derivative. So now we're going to do our dot product. So doing our dot product, we get negative sine squared t plus cosine squared t, which equals the cosine of 2t. So now what we can do is we can now integrate going from 0 to 2 pi of cosine of 2t dt. Pretty simple integration there. I think everyone knows how to do that. But notice what happens when we put in the 2t. We get the sine of 4t, which is 0. We get the sine of 0, which is 0. So we just get a value of 0. Which means that if we do this here, we should also get 0. So in this case, this is one where it's a lot easier to do this one than it is to do this. That's oftentimes what happens. A lot of times when they pick ones where it's easy to do both ways, it's actually easier to do it this way. But there's a lot of these that are a mess, and then it's actually an advantage to do it using the curl. So let's go ahead, let's take a look. So the first thing we have to do if we're going to take the integral of the curl is we have to find the curl. So we're going to use our formula that we memorized for curl. So remember, this is our f right up here. So our curl, first to find the y component, we won't take any derivatives, to find the zx component, we won't take any derivatives of with respect to x. So what we'll do is we will take the derivative with respect to y of our first, which will be 2y, minus the derivative with respect to that, which would be z, so we get 2y. Then, to get our y component, we won't take any derivatives with respect to y, and we have to reverse it. So we'll start with the derivative of y with respect to z, which will be 0. And then we'll take the derivative, subtract the derivative here with respect to x, which will be minus 2x. And then for our last component here, we'll take the derivative with respect to x of the y component, which is 1. And then the derivative of y with respect to y is also 1. So I get 1 minus 1, I get 0. So that's my curl. And now what we'll go ahead and do is now we'll go and we need to parameterize the surface. So just like we parameterize the boundary curve, now we have to parameterize the surface. In this case, we're going to use, it's a sphere, so we're going to use spherical coordinates. The r, we don't have to worry, the r is not varying. So we can just go ahead and use our theta phi. So we know that we've got our surface parameterized like this. And we know we're going between 0 to 2 pi for theta. But remember, phi, we only want the top half of the surface. So we're only going to go from 0 to pi over 2. If we wanted the entire sphere, this would go from 0 to pi. So there's our surface. Okay. So now what we have to do is, in order to do this, this operation here, we must go ahead and we must find the normal for the surface. So in order to find the normal, we have to find the partial with respect to theta and the partial with respect to phi, and then take the cross product. So we're going to find the partial with respect to theta. So doing that, we should get this. So we should get our negative sine theta, sine phi, cosine theta, sine phi, and then 0. And then we take our partial with respect to phi, and we get cosine theta, cosine phi, sine theta, cosine phi, and negative sine of phi. Then we need to go and take our cross product. So taking our cross product, we get this mess. So I think, and by the way, I didn't write out the matrix, the little array, because I think you can see the way I did this is I imagined I had an I, J, and a K right over this. So to get the first term, I just kind of covered this up and multiplied across this way and subtracted going across that way. So I was quick to see I had a cosine theta negative sine phi, and it was minus 0. So there you see my cosine theta negative sine phi, which just became negative. And then I set this up here, went across this way, became a positive sine theta sine phi, but then it has to be negative because I'm subtracting whatever that's going to be, and then 0. So that becomes the minus there. Then this last one becomes kind of messy, and I expressed it out here. Notice what happens though if I factor out a negative sine phi, cosine phi, I just get sine squared plus cosine squared, which is 1. So what I really have is a negative sine phi, cosine phi in this last spot here. So I end up with this expression here, and I shouldn't have a so anyway, I have that I think I may have got a mistake with my 2 there. We'll check and see. All right. So, but I'm certainly not going to start this all over again at this point. So I'm going to do curl, and yeah, I think that this, so curl, what happens, there shouldn't be a 2 here. Should just be, that, oh, I see what it is. There shouldn't be a 2 there, but notice this is negative, and I know this from the problem. It says that I need an upward pointing normal, which this would make my z negative. So in this case here, I'm going to need to make sure that this needs to be a positive value here to get my upward pointing normal. So I am going to have to change this here. You notice where phi's between 0 to pi over 2, these would both be positive. So in order to get this positive, I have to multiply the whole thing through by negative. So that's why these signs all changed. Okay, now I go and I get the curl. And I get the curl of the function with this substituted in. So I already found the curl. Remember, the curl is up here. And now what I'm going to do is I'm going to substitute in. So I have 2 times y. Well, I know what my g function is here, so it's 2 times this. So I substitute in. And I've got negative 2 times my x, which goes right in here, and my z is 0, so that's just 0. So there's my curl with it parameterized there. So before my curl was in terms of x and y, now it's parameterized. Now from that, I can take my curl and dot product with my normal. So here's my normal vector. Here's my curl vector. Do the dot product, and what you see here is you get 0. So I have now verified if I take the integral of 0, I'm at 0. So I don't even have to worry about going any further with my double integral. It's going to be 0, verified the same as that. Okay. 17.2, 1 through 9 odd. And yeah, do your best with these. Consult the solution manual as needed, and we are going to get to spend a couple days in this section, so hopefully it'll start to click and make a little more sense as you do it more. But like I said, 1 and 3 are easy, so you'll enjoy those. All right, sounds good, and we'll plan on, unless something comes up, we'll plan on seeing you again with videos next week.